Hello. Today I'd like to talk about databases. To utilize the industrial plant genome, we have to know what kind of database is existing in a web environment. For example, first of all, I will talk about Python. So Python is kind of a web portal hosting a majority of well sequenced plant genome. So if you look at this here, is now Python 12. So it started from, of course, version 1 and now 12. So it has a lot of sequences you can see here. So these all names are, majority of them is plant, and some of them is algae or moss. I think you can see it from blast. Okay, so blast gives you very simplified tree here. So you can see the big clade of the classification. So BDD plante, and it includes green plant. But here, these species are not actually plant. It's kind of so Piscomitella, for example. If you search Piscomitella pattern, then you can see it. It is not a plant. It's kind of okay, a moss. Okay, so it's a moss bryophyte. I use as a model organism for studying on plant evolution and development and physiology, of course. Yes. So it has a lot of genomes that you can use study plant evolution, or you can search any genes or proteins that is included in each genome. Also, it has another things like a chlamydomonas and Burbox, and these are all algae. So you can chlamydomonas Reinhardti is like this. You can see, click on Wikipedia. So this is very interesting species that it has a flagella here, so it can move around, but it also has what is that? Chloroplast in there. Yeah, it has a large cup-shaped chloroplast, so it can move, and it can also photosynthesis, and it is a single cell green algae. Very interesting species. So to do some comparative genomics, you have to understand how to use this kind of database. So I will explain today how to use this database. Because of this is industrial plant lecture, I will select laboratory. So laboratory, where is that? Ricinus. Yeah, Ricinus. So Ricinus is, they are saying that castor no, this is not, this is another thing. Okay, what was laboratory? Laboratory habit. I thought that they have laboratory there. No? Okay. I was thinking weird manner. So this is oilseed castor bean, but this is familiar with the rubber tree. Okay. Okay. They don't have rubber tree genome yet. Let me check because this is very important tree for genome. Yeah. Oh, yeah, there is rubber tree genome in nature. Nature plant. So I don't think they posted this data in 파이토종 yet. Hebia. Let me see Hebia. H. No, there is no Hebia. Okay. Then where did they put the data? Okay. Okay. Acknowledgement. No. Is that recording or? Yes, it is recording. Okay. Okay. So has been deposited in GenBank with this number, right? I doubt. Okay, it has. So you can go to assembly. So I was thinking that now I'm explaining Python, but now I'm explaining NCBI. Okay, now we have a robot tree. And we can see the information of this robot tree assembly. So you can see they are assembled using this software, and the coverage of genome is almost 100x, which means they produce 100x sequence data to assemble this genome. Okay. So scaffold M50 is 1.2 megabytes, and the size of genome is 1.3 gigabytes. This is a bit large to assemble, so they successfully assembled their genome into 1.2 megabytes of M50. So what is M50? I will explain M50. This is a bit mess to explain everything in the middle of lecture, but it is okay because this is online lecture. We have a lot of time. M50 means, so is there any picture or not? I think we can see it through the picture image. Alright, so what is the M50? So if you sort all the contiguous with regard to the length, then in the middle point, so this is horizontally arranged, but when you calculate the M50, you have to vertically arrange. Vertically paste each other after you sort the contigs. Then you will have whole length of the sequences. Right middle point of the sequences indicate that it is the contig you will calculate the M50. Okay, so you grab the contig and measure the length, then the length is M50. So this is kind of a representative assembly length. Actually, if it is long, very long, then the assembly is very have a high contiguity. So if you don't assemble a lot, then the M50 value is decreasing. Okay. So there each genome size is 1.3 gigabase, but the M50 value is 1.2 megabase, so it is quite okay. So for me, it's really good. So how do you download this data? So you can go to FTP directory for the left-seq assembly. Click on there. Okay. Then you can see many information of this data. Okay. Then you can download. Where is it? So this is a gene model. So I will download this, and I cannot see the genome. Primary assembly. Stafford. No. I cannot see. Here. Genomic FNA is the reference genome. So now we downloaded two components. One is gene model, the other is genome sequences. Okay. Then you can open up this data through the Linux environment. Okay. So last time we already set up the Linux environment. So let's open the Linux environment. Okay. So it takes a lot of time yet, but I will open first of all the gene model. So I'm thinking that we have to first move the data. So this is the data, Control X, to the C drive, and we're making new folder. Okay, industrial plant. Oh yeah, we already have it here. Okay, so paste. And let's go to the folder I plant. Then you can see here our data. Right. Then LESS. I will show you again. Less is the command, Linux command, show you this text data. Even though it is compressed using Gunzip, less can open it up. Okay. Okay. So you can see this is the GFF version 3 and has some informations, and you can see many genes here. Okay. So in this config, NW blah blah blah, and this location there is gene. Okay. Within the gene location, and this location almost exactly same as it, this is mRNA. Sometimes it is deeper. And within this region, you have exons. Okay, you have exons. So you can see the exact location of exons, right? So maybe sometimes it is deeper with exon and CDS because exon include the UTR, so 5' UTR and 3' UTR is usually included in exon. But CDS only include the protein coding region. So coding sequence is CDS. So the location of CDS is well described here, right? And so these information actually show you how these information associate each other. So this ID is axon, right? Axon and blah blah blah, but its parent is this ID. Okay, so where is this ID? This ID is right here. So relationship between mRNA and axon is like a parent and children. Okay, so the parent of mRNA is the gene. Right? Gene. This is the way they organize this GFF format. And also, it shows you the annotation. It's really good. Okay, then let's analyze more. More bioinformatic manner. So open up the Jupyter app. It takes time. Okay, what is that? Okay. Let's use sudo permission. Jupyter. Allow root. Okay. Okay, now we are opening what was that? Laboratory genome analysis. Import pandas. Does it have it or not? I don't think it has pandas yet. There is a pandas. Okay. Then open. So if you don't have pandas in there, then you can install the pandas. Conda install pandas. Okay. I don't know why it takes this time. Anyway, I will show you the result later on. Then you can open the file of gene model. So gene model data frame, gene model equal with CSV. GCF was the file name. And it is compression is gunzip. Okay, and separation is tab, and comment equal shop, and header not Okay, it is well loaded gene model and head. Then you can see more beauty way. Is that right? So you can see the gene and mRNA and exon and so on. So I put dot head method here. So you can see only top five information. If you put here 10, then you can see the top 10 information. If you think that I want to see the statistics of the gene contents, for example, then you can use these information because it has all the compounds of the gene contents. So you can use. I forget. Value count. I said value count. Oh, okay. So value count gives you what kind of information is residing, what kind of information is existing in this gene model. So let's see. So total 38,000 genes, 38,000 genes are there, and mRNA, 57,000 mRNA are there. This is quite normal. So this is quite normal number of genes and mRNAs for 1.3 gigabase genome. That is laboratory. Right? So, and it has, I don't know why they have another feature, transcript, but if you are interested in this feature, then you can select it. Okay, I think it is related to this pseudogene. Okay, so sometimes I really wonder how they determine the pseudogene, even though they don't express. Still, there is a chance to be expressed with regard to special triggers outside. So I don't really like saying that it is pseudogene. So this is my opinion. Okay, so you can check in this way, and I don't know if they can plot it. Okay, they can plot. Then I will show you how to plot the map plot live in live. Then you can plot it. So this should not be line chart. You have to say exactly bar chart. You will use bar chart, right? And you have to map plot live by plot. PIT. So you can install pandas in this way, but I already have pandas. So I will not install it. And if you want to install matplotlib, then you can learn in this way. Okay. Let me change the theme. This theme is better for you, I think. Okay, so following this tutorial, you can generate this bar plot easily, and you can add variable count. Right? So there is now it has count, and you can save it. Save pig here. Save pig and laboratory gene model component count. If this is too long, but I don't care. Okay, B box and inches tight. Why do you do B box inches tight? So if you don't do this, then sometimes your saved figure cut in middle of this way. Okay, if you want to include everything, then you have to put this argument end of the command. Then save. Let's go. Then now you have this stuff, very big one. Okay, this is high quality PNG, so you can use directly for your publication, right? So because I put DPI 200. Good. Okay, so this is how you analyze the data, gene model. But let's go to more on that, because if you are interested in long non-coding RNA, then your feature value should be long non-coding RNA. Is that right? Okay, then you can mask it. So what are you doing? So let me see you again. Let me show you again. So second one, the second feature gives you the type of element. So I said that is that the second component is same as I asked the Python. If the second component is same as long non-coding RNA, so it says most of them is false, but it is abstracted a little bit. So in the middle of this part, some of them is true. So now I have this M variable containing all false or true, so I can mask model with the M, right? So how many shape? So 4081. So this is almost 4081. So now we have all non-coding sequences. Okay, right? So no, these are all long non-coding sequences. Okay, so I will put here long non-coding LNC. So yeah, right. So you have information. Then let me check what kind of information do they have. So you have here, this is index number. So you can grab this information using this index number. Then you can see here it has special information at the ace column. Okay, then you can read the exact information of this long non-coding. So I have problem to distinguish R and L. So long non-coding RNA. So actually I can read okay, it is uncharacterized yet, right? But I want to see if they have something really annotated or not, right? So okay, then we will see the annotation. So product have maybe. Let me see. Let me check another thing first. So let's check. So for example, gene may have the information, right? Gene have any info. It doesn't have at all. It doesn't have at all. Okay, hold on. 2. Okay, mRNA have it. I think product have the annotation. Let me check. So we will grab mRNA also. We can grab mRNA. It's like a long non-coding RNA, gene model, and M, gene model, mRNA. Okay, mRNA. Okay. Then it has. Let me check the 15 one and 8. Okay. So right, product is protein detoxification 24 like. So then now we can understand that product have the annotation. So going back to long coding RNA. So if you click on here, push B button, then you can add many blank boxes. What am I doing? Okay. Let's parse 8.1. So eighth column is selected. Then we will apply some kind of function. So this function is determined by lambda grammar. So x should be so this value goes through x. Then we will split the value with this one. That's right. With this one. And maybe we will this bit complicated. Then let's make a new function. Info parse. So we will make new function info parse info parse. Okay, x equal to x for x for I. This is not good, but it's okay. I split by this one. No. Sorry. For each in x split semicolon. Then we will we'll add list. How do you name it? List. That is information, right? List info. So we will add list info. Append each split equal. So we are splitting this equal, right? Then I think we can directly return dict list info. Then let's check what can we do with this information. Okay, hold on. Okay. Values. So first values equals, we will supply this information to here. Okay, func parse. Okay, it gives you back the information in dictionary. Is right? Okay. Then we can apply this. Then now we have a lot of information, but what we want to have is, what was that? Product. So product. So we add product there. Function files are not so. Yes, it is right. So remove it, and return product. Okay, then now we have here so many annotation here, but majority of the long non-coding stuffs have no characterization, I think. Let's make this into comma separated version. Because if you save in this way, you can open up in Excel. Maybe you can use to Excel, but I prefer using this comma separated version. So number 3 long non-coding RNA CSV. You can save it. Okay. Then open it up, and you now you have a lot of information. So open using Excel. Now you have a lot of product transcript variant. Actually, I don't care, but it has no annotation at all. No annotation. That's right. Okay, no annotation. So that's why people really like long non-coding RNA, because we do not know about it at all. Then maybe you want to extract the sequences of this long non-coding RNA. Okay, we can see this genome data is well downloaded here. Yeah. Okay. Move. Okay. Here we have FNA. Let's open it up. Of course, you can open directly with gunzip, import gunzip, but I don't want to mess up your study here, because it will be complicated for now if you try to use gunzip. So I will first of all extract this file first. Okay, so I usually using my module Kang, but these do not have Kang here. So I'll make definition of pasta to dictionary. So file name. So first of all, I will open this file name, and file read, and we will split the. So when you open the pasta file and read, then everything is in this fr. So every letter in your pasta file will be in fr variable. So we will split variable with this symbol. In Korea we call it kokse. Okay. So actually kokse defines each element of the pasta file. So I will use iteration for loop to extract every element of the pasta. So I'll open up the dictionary here, blank dictionary, and let's extract the header. So you have to imagine what happened in pasta file. So I believe people who attend my last lessons, lectures, including 원예 생물 정보학 and or the undergraduate classes by Python or by big data, then people understand this very well because they I provided this information very well at the time. Okay, so header. What is the header? Header, title of the sequence. Header will be each split enter string sequence in each split. Everything should be attached without any space. Then dictionary string header equals string seq. So I usually do not make the variable in this way, but I heard this is very important for the app development. So I'm trying to make well organized variable scheme. So return dic. Then let me check. Let me open dictionary pasta to dic. Here GCF FNA GCF FNA. Open it up very quickly. The reason why it is very slow, I think because I'm working on my laptop. Usually I use the server to doing this job. Let me check the usage of the memory. Oh yeah. Okay, but we have it. So we can, for example, so now we have this variable. Memorize it, dicpa, and where is it? And head. So this sequence is necessary to retrieve these values, these sequences, right? So dicpa and grab this and this number, right? But you have to be careful with this. You have to always extract one, because these values based on, starting from 1, but in Python it starts from 0. Okay. I have to check it. I know what's happening here. See up here. If you open up it, see the name have lot of unnecessary information, so I will cut this out. Okay, I will cut this out. Then this header should be like this. Then reload. To my laptop. It's a hard time today. Okay. So it's uploading. So this is why you have to have your own server, having, for example, 120 gigabytes memory. Okay, now we have it. And let's check this again. Then we have sequences, right? So we have sequences. We could retrieve the sequences from this information. Okay. Then I don't want to do this manual way, right? We don't want to do. Nobody want manual way. So let's grab. Let's update the sequence. Sequence. Yeah. Sequence will be. We have to apply lambda x. So we can do this lambda. Dic part. So so zero column will be the config name, and the region start from 3 to 4, right? It should be -1. This is really messy, but it will work. And axis should be 1. What is axis? So this number, when you refer this number as horizontal manner, then you have to put axis 1. If you refer this number in vertical manner, then your axis will be 0. Then yes, click enter. Okay, everything done within a second. Okay, it has sequences. Is that right? So we have sequences. So again, let's save this information to here. 자르기. Right? Let me remove unnecessary information. Necessary information, and I will erase this also. Okay. Then now we have number 3, non-coding RNA information. Right? So this is really easy, not that difficult. Okay. Then we have sequences. So if you want use these sequences, then you can just you can design primer or design. You can just grab this information or like this and blast it. Let's go to NCBI again. NCBI again, and go to blast. So this is how you actually playing around with the sequences. So even though you don't have any idea with this industrial plant. Just grab any sequence. Just grab any sequence to blast it. Okay, so blast it. Then you will. The NCBI have a great database calling nucleotide collection. So just type blast. Click on it. Okay. Then it gives you first of all, yeah, of course we have all this is interesting, right? This is really interesting. So actually we are thinking that this is long non-coding RNA, but originally it is similar with this disease resistance protein. Like this. So this protein is all similar with this long non-coding RNA. So we are thinking that this is a long non-coding RNA, but maybe this is another variant of disease resistance. Actually, the genes providing disease resistance have a high rate of evolution. So it have some kind of evolutionary mode that accelerate the speed of the evolution. So maybe that's why it looks like non-coding, but it was coding sequence. That's what I'm thinking. Okay, interesting. Okay, what time is it? I spent a lot of time already. Okay. But I will do a bit more. Okay. So what I was thinking is that starting from phytosome, but I explained NCBI first, right? So I will explain phytosome again. So in phytosome, so there is a resinous communist, right? So castabin. Castabin is in Korean ajukari. So ajukari is very interesting species. Actually, it gives you oil. So when I was student, I was participating in the constructing the genome of Jatropha. So we have Jatropha genome. So 정민하 published this Jatropha curcus, the genome sequence of Jatropha curcus, which provide the biodiesel plant. But this is a very important industrial plant. So where is my name? Here, Yang Jae-kang, okay, Ha Jung-min, right? So my 스승님, 리석하. Okay, so this is very interesting plant because you can directly extract Jatropha oil extraction. So let's go to image. So it is really interesting because yeah. Slow. So this you can see here. This is a seed of the Jatropha, and it just grinding. It's not grinding. It's like a pressure. Give them high pressure. Then you can extract these oil, the crude oil. But this crude oil can run any I heard that the scooter, for example. Okay, so the oil directly extracted from this seed can run scooter, 오토바이. 여러분 아시죠? So this is very useful plant where people have to learn agriculture machine with a very cheap oil expense. So this is very important. So this Ricinus communis is neighboring species of this Jatropha. So Jatropha is tropical plant. However, this Ricinus communis is also living in Korea. 아주까리. Okay. 아주까리. 아주까리. So 피마자. 아주까리 피마자. So there is right. So neighboring species in Korea. Then we can maybe you can raise a question: what kind of evolution is happening in the Ricinus communis or Jatropha crocus, right? Because Jatropha crocus can living in only tropical region, but Ricinus communis can living in a very mild tropical region like Korea and Japan or China. So maybe you can want to understand what kind of evolution is happening in this genome. Okay, so you have to, for that you have to download the data. If you want to download data, then you have to click on bulk data. Okay, proceed the data. So they are saying that if you use this data, you have to cite this paper. Actually, they are happy because they publish their result in the Nature Biotechnology. Nowadays, we cannot publish this genome data in Nature Biotechnology. It happened only 2010. Year. How do you say? I don't know. Yeah. So you have to log in first to download it. So let's log in. So I already have it. So let's sign in. And then let's go to Ricinus communis. Bulk data here. Okay, proceed to data. And it has special file management system and a Python, which is very slow. So maybe if you cannot open this file system, then you have to go to NCBI again. Then you can open up the data. So first of all, you have to open up the assembly. Then you can download this pasta file. This is genome data. Okay, click on it, and you have to download annotation. Where is the annotation? So this is a whole annotation gene.gff3. So you click on it. So check and check. So you have to check and download selected file. What is the meaning? I don't know. Okay. So wait for a while. I'm finishing my video for now. So you have to wait for a while. So anyway, so I think it takes a lot of time. This is too slow. So what I was trying to say to you is downloading pasta and GFF is exactly the same as what we have done. Where is it? What we have done in here, right? So this is the pasta, genome pasta, and this is the GFF, right? And you can check what kind of distribution of exon and CDS mRNA gene, and you can select a certain feature, and you can make the CSV file containing every sequences, right? So after downloading this listeners communist data, then please apply this code to listeners communists again. Maybe I will explain again the next time with listeners communists. Okay, thank you. Bye bye.